We're going to solve this entire question using absolutely no numbers. So in our first conversion, what we're trying to do is get that grams of fluorine gas into atoms of fluorine. So we have two options. We can either focus at our answer and saying that I want atoms of fluorine up top, and I ideally want to get rid of grams of fluorine gas on the bottom. Is there a direct relationship between grams and atoms? No. Okay. Grams is a very massive quantity in comparison to atoms. So this is our decision point. We don't have a proper conversion between those two. So we either erase atoms of fluorine or we erase grams of fluorine. Most people, which I appreciate because I'm the same way, would erase atoms of fluorine. Okay? It's not wrong to do it the other way. Okay? It just tends to be easier. Why does it make it easier? Because what happens? You can immediately cross something off. People tend to be happy about crossing something off. That's less to worry about. That's why we make lists of things and we check them off. Okay? Feels good. We got rid of something. Okay? So what can we convert grams of fluorine to? Moles. Okay? Almost. We actually can't convert grams of fluorine to moles. I can convert grams of fluorine to moles of fluorine. We have to be worried about the full unit. Okay. I'm now at a new question. My question is now moles of fluorine into atoms of fluorine. Okay. Can I do that conversion? Yes. What we're saying is what needs to show up on the bottom? Moles of fluorine, and what are we hoping at the top? Okay. Ideally, we get atoms of fluorine. Where's that conversion? So I heard a bunch of people say that we have this conversion. Please tell me what that conversion is. 1 mole of atoms, or 1 mole of eggs, is equal to 6.022 times 10 to the 23rd eggs. 1 mole of fluorine, F2, should be equal to 6.022 times 10 to the 23rd F2. Is F2 the same as F? No. No. We do not have this conversion. Okay? So, the conversion that we do have is we can convert that into F2. Okay? This is where being careful with your names can come in handy if you really wanted to. We could call this atoms of F2. That's not officially true because F2 has 2 atoms in it. That's a molecule, not an atom. Okay? So I would call that a molecule of F2. If we go through and look at our unit conversion, we'd have moles of F2 now cancel. I now have the question of molecules of F2 in comparison to atoms of F. Are those the same unit? No. Is there a conversion? So again, molecules of F2, atoms of F. Is there a conversion between those two units? What is that conversion? Don't quite accept 1 to 2. 2 atoms of fluorine will equal 1 molecule of F2. And it wasn't a dispute with 2 to 1 or 1 to 2. I don't care about that. I want to hear the units in that. Okay. So now that we've tracked our units all the way through, molecules of F2 cancel, we'd have atoms of F2. So let's be a little bit more careful now, and since we started to drop numbers in, so we dropped it in our last part, let's drop it in reverse. What numbers go into that conversion?
1 in the denominator.
One should be a little bit more careful than saying 1 in the denominator.
1 by moles.
1 by moles, because our conversion factor is 1 mole equals 6.022 times 10 to the 23rd. Okay? So we would have 1 mole of F2, and then we have that lovely long number, 6.022 times 10 to the 23rd. Okay. Molecules of F2. We move 1 step further back. Where's our relationship from grams to moles? I'm just writing some other stuff down. We'll talk about that in a second. Where do we find information about grams and moles?
Periodic table.
Our periodic table. So we can go to the periodic table. And what does our periodic table tell you the mass is for fluorine?
Fluorine what? Fluorine gas or fluorine?
We got to be careful. Are we looking at fluorine gas or are we looking at fluorine the element? What does our unit tell us? I'm looking for fluorine gas, which is F2. The periodic table tells us the mass for F and only F, which means we need to calculate our molar mass from our, I'm in a spelling issue again. That's totally not it, is it? I'm going to trust you. From our periodic, is that really it?
It's right there. On both sides of the ring.
Touche. Fluorine has what mass? 19. How do we get it to F2? Multiply by 2. That gives us the number of 38, but what are our units? 38 grams per mole. Where do I put my numbers in? Where does the 38 show up? 38 in front of the grams in our calculation, which means we have to put the 38 here. And our mole, what number shows up in front of the moles? 1, so it doesn't change the number. We've now done our conversion across. Okay. So it's a question of finding all of the conversion factors and putting them in appropriately. Okay. Chapter 8, Chapter 9, that's all we're doing. Where's another conversion factor? Oh, here's a conversion factor. Use it. Okay. Does that conversion factor get you closer to what you want as an answer? Yeah, then that was a good use. Did it take you further from that answer? That was a bad use. Okay. Periodic table gives you what units? Okay. What conversion factors come from our periodic table?
What doesn't come from our periodic table is a question.
That's a good question. It's our molar mass, which is going to be grams per mole. What else could come from the periodic table? The AMUs,
Number,
the atomic mass
element
per
symbol.
atom, conversion factors. What is Avogadro's number? I see your hand. Give me a second. Avogadro's number relates a mole to 6.022 times 10 to the 23rd. Probably can't tell it says 23rd, so I'm going to rewrite that. 23rd units. So a mole of units equals 6.022 times 10 to the 23rd units. We're counting things like eggs. And then our formula allows us to convert one substance, or let's call it this way, we have to go with substance. One substance related to another substance. Okay, hand, Andrew.
I was wondering, if I do the molar ratio before I find the unit, is that wrong?
Does it matter the order in which we did this calculation? No, it's completely irrelevant. We can still solve and get the correct same answer. As long as you are adjusting your units in the correct place, you're fine to go all the way through. Okay? Where it becomes tricky is if we shifted, say, that last conversion, 2 atoms to 1 molecule of F2, and we did that calculation first. Do any units cancel? No, I can't cancel grams of fluorine with molecules of fluorine. That unit doesn't cancel.
I just did second.
So if that does first, it's not that it's wrong, it's that we don't get that nice little happy cross some stuff out. Okay? So I tend to organize it in a way that I can cross stuff out because I then feel better about myself because I've removed something to think about. Okay? If you don't need to feel better about yourself, then good for you. You suck. Dang it, I recorded. Okay, questions? Okay. So, we ready for more? Why not? Let's do more. first thing we would like to do is see if we can do this direct conversion across. Molecules S of 2, 2 grams of SO2. Do we have a direct conversion between grams and molecules? That conversion does not exist. So what we need to do is convert those molecules of SO2 into something else. Why do I pick molecules of SO2 to convert? Because I want to cross it off. Okay, but before I can cross it off, what is going on here? My screen just went blank. What is happening? How weird. Okay, well, one molecule, SO2, is it actually writing?
Yeah.
Okay. Molecules, SO2. What can I convert molecules of SO2 to, for lack of a better word? Moles of SO2. What is the relationship between the moles of SO2 and the molecules of SO2? 1 mole is 6.022 times 10 to the 23rd molecules of SO2. What happens with my units? I now have moles of SO2. It's not my final answer, so again, I want to set up another conversion. Do I have a relationship between the moles of SO2 and grams of SO2? What's that? Where's that conversion factor found? I'll accept 2 answers. Okay, I think I saw one with a gesture, periodic table. The other way it was gestured was, it's in the question. Okay, we tell you that it's 64.07 grams per mole. Where does the 64 show up in front of? Grams. So what number needs to show up in front of grams in our conversion? 64.07. What number shows up in front of moles? 1. What happens? Moles of SO2 cancel, and now what we've got is grams of SO2 as our unit. Punched into the calculator, we now have our answer. Simple, right?
Can you punch it in the calculator though? Because I'm not sure if I'm getting the right answer.
Give me a calculator. Okay, so first check on this that can be helpful. What would we expect for a number? Really big, really small?
Really small.
Why really small? I'm looking at one molecule. Molecules are tiny. So what should the mass be? Really, really small. If it's not a really small number, then I probably did something wrong on the calculator. So when I go through and do this, I get the answer of 1.06393, a bunch of other numbers, times 10 to the negative 22.
See, I didn't do it right.
And we can talk about why you didn't get it right in a second here. Is that going to be your final answer?
No.
No, what's wrong with it?
Sig figs.
Sig figs, I agree. How many sig figs should we have? That one's a bit dicey. Yeah, we really only need 1 sig fig because we were given 1 molecule. Okay, so 1 times 10 to the minus 22. It's a pretty crappy question, in all honesty, okay, for that reason. Okay. This is still going to be a wrong answer. What's wrong with this answer? We don't have the unit. Grams of sulfur dioxide. Okay. Next thing I'm going to go through and do is show what's happening when you enter it into the calculator. So what I would go through and do is take everything in the numerator. We love color coding, so let's color that in a blue-red. And I get 1 times 1 times 64.07. Well, that was kind of boring. I get 64.07. Okay. What do I get in the denominator? 1 times 6.022 times 10 to the 23rd, okay, in my denominator. When we go to enter this into the calculator, your calculator, at least most calculators, do not give you this numerator-denominator format to enter something in. It's all linear. So how does it get entered into our calculator linearly? we take 64.07, and then we can tell it to divide. What does your calculator do? You got a little division sign. Divide 6.022 times 10 to the 23rd. According to the order of operations, what's your calculator think you're doing?
Multiplying 64.07.
You're doing that division, and then you are multiplying that by 10 to the 23rd, which means the number you're going to get will be very, very big, which should be an immediate response of, oh crap, I did a calculation mistake. Okay. How do we prevent your calculator from doing that type of calculation? You need to make sure that the calculator does this calculation first. Put parentheses around that part of the calculation. That should set you up with the correct answer, which I'm going to guess was the mistake you made. Okay. Simple mistake. Worst case, drop lots of parentheses. Everything will be nice and clean. Questions? Everybody getting this? Seeing some yeses, that means it could get difficult. How many moles of CO2 are necessary to make 1 mole of sodium hydrogen carbonate? Set it up. Same idea as before. So, just like we've been doing before, write down what we want, write down what we start with, start dealing with our units in between. For those of you that did it in your head, good job. Moles of sodium hydrogen carbonate, we need to get rid of, so that unit needs to show up on the bottom. What unit do we want on top? Moles of CO2. This is a bit tricky. Everything we've looked at up to this point is converting the same substance. Grams of a substance to moles of a substance, atoms of a substance. We've not been changing from substance A to substance B. Okay. To do that, we need one thing. What is that one thing we must have to convert between substances? You must have a balanced chemical equation. Without the equation, you cannot do this conversion. So how does that help us out? What numbers need to go into this? Well, what number shows up in front of sodium hydrogen carbonate? What number shows up in front of CO2? What happens when we check our units? And we end up with moles of CO2. So we punch it into the calculator, we get 1 times 1 is 1 divided by 2, which gets us half a mole. This is an interesting question. How do we get half of a molecule of CO2? It's not half of a molecule of CO2. I can't get half of a molecule of anything. That's not possible. I'm not looking at a molecule, though. I'm looking at half of a mole. A mole is a massive number. Can I get half a dozen? Yeah, that's absolutely fair to do. Okay, I can do the same thing here. Okay, make sense? What's the next one? Ooh, fun. What is the mass in grams of sodium hydrogen carbonate produced when 2 moles of CO2 are consumed? What do we want for an answer?
Grams.
No, we do not want grams. What were you adding, Lizzie? I think you started adding something else. We wanted grams of sodium hydrogen carbonate. Okay. Just the mass is going to be completely useless to us because we could be calculating the mass for anything. We're calculating the mass of the moon. That's not relevant to the question. I don't know. A big number. Okay. So what do we start with?
Moles of CO2.
We start with moles of CO2. How many moles of CO2 do we start
2
with?
moles of CO2.
Right, so now we start our conversion process because moles of CO2 is not the same thing as grams of sodium hydrogen carbonate. So what unit needs to show up on the bottom?
Moles.
Moles of CO2. Okay. So we want that unit to cancel, which is why we're using it. Okay, but before we can get it to cancel, we need to convert it to something else. What can we convert the moles of CO2 to? Why convert to moles of sodium hydrogen carbonate? Because I can convert moles of CO2 to grams of CO2. That's a perfectly valid calculation. I can convert it to atoms of CO2. Why do I go into moles of sodium hydrogen carbonate? I can get rid of the CO2 with any of those conversions I just talked about, but it's trying to get closer to my target. My target is sodium hydrogen carbonate. So my conversion needs to somehow start getting me closer to that. By going into grams of CO2, I may be at grams, but now I have no way of converting grams of species 1 to grams of species 2 because our equations don't give us that. How many bicycles can you make if I give you 2 bicycle tires? 1. How many bicycles can you make if I give you 100 grams of bicycle tires?
2.
Right? You'd have to know the mass of a bicycle tire, and more than likely it's not even 1. Okay. You don't have that conversion factor. You don't have that information. That has to be brought in as extra information. Our equation tells us just the number of these things, not the mass of them. So we could convert this now to moles of our sodium hydrogen carbonate. Where do we get those numbers from to match those units? From the equation. What number shows up in front of sodium hydrogen carbonate? 2. What number shows up in front of moles of CO2? 1. We track our units. Moles of CO2 cancels, and we end up with moles of sodium hydrogen carbonate. Is that our answer?
Nope.
Nope. So we have to do yet another conversion. Moles, yes. Sodium hydrogen carbonate on the bottom, and we need grams of sodium hydrogen carbonate on top. Is there a way to relate the mass to moles of the same species?
Yes.
Where's that information found? In the periodic table. So we go back to the periodic table and we start to deal with a whole bunch of extra math that I did not intend to actually do, but 23 plus 1 plus 12 plus 16 times 3.
168.02.
Where did I get all of those numbers?
Periodic table.
So the periodic table gives me 23, 1, 12, and 16. Where did I get the 3 from? There's 3 of oxygen in the formula. That should give me some number. That number is the grams per mole. What number shows up in front of grams? 84. What number shows up in front of moles? Punched it in the calculator. We now have our answer for grams of sodium hydrogen carbonate. Okay? Kind of makes sense? The next one. Oh, next one is saying chapter 9, which is already what we've been talking about. When we look at that balanced equation, okay, all of this information falls out of that equation. We have to do some conversions to get them, but the primary ones that we're going to be concerned about, okay, so I'm going to erase the stupid ones that the textbook shouldn't have provided. We don't care about that one. We don't care about that one either. So we only care about the top one and the bottom one. That information is what our balanced equation tells us. It tells us or gives us a way to convert between the molecules of one species to the molecules of another to the molecules of another. But at the molecule scale, can we do an experiment down at that level? Sure. We can't physically move one atom to another atom. We don't have the ability to do that. So we have to take a big solution of atoms and a big solution of other atoms and we mix them together. That big solution is now a much larger amount. That larger amount tends to get up towards the mole amount of atoms, or the mole amount of molecules. Okay. So that's why we bring in that mole number. Okay. Since we've got this equation, that gives us all of those individual relationships, which we can then turn into conversion factors. So if I wanted to use this very first one, what does that conversion factor allow me to convert? What to what?
Oxygen to nitrogen.
Moles of oxygen into moles of nitrogen. Why is it not moles of nitrogen into moles of oxygen?
Because oxygen's on the bottom.
Oxygen's on the bottom. So what we're evaluating is what's on top. That's what I can convert into, is whatever's in the numerator. Okay? Any one of these is perfectly valid. Why would I choose one over the other? It's what I'm looking for an answer. If I want to know the moles of nitrogen, does it make sense to use that lower right-hand corner conversion factor? No, because nitrogen's not in that conversion factor. So we have all of that information, and we get to decide how we want to use it, okay, depending on what the question is asking us to go through and do. Okay? So how many moles of oxygen react with 2.25 moles of nitrogen? Is this a question that you guys can answer? What are we trying to do? Our answer needs to be what? Moles of oxygen. What do we start with? Moles of nitrogen. Somehow in the course of this reaction, what do I need to do? I need to convert nitrogen into oxygen. How do I do that conversion? A ratio that comes from an equation. Are you given an equation? How many of you know the equation? Okay. If you don't know it, you need to have it. Okay. So it's something that should have been given to you. So we could set up our little conversion and we could go through and run our calculation. Okay. All we're doing is taking those same units, setting up our conversion factor, allowing for our cancellation of our terms. Okay. We can do these until we're blue in the face, which is probably a good idea to do before the next exam, okay, for you. Well, I don't want to be blue in the face. Okay. Questions? Okay. I should have deleted some of these slides. Okay, so if we looked at formula usage, okay, it comes back to looking at bicycles. Okay, we can switch it up and look at bicycle wheels. To build a wheel, we need spokes and the rim. Do we need the exact same amount of spokes as we have rim? No, it's not a 1-to-1 ratio. It depends on how many's in there. So we can generate a formula to build that, okay, to build a wheel. Once we know what the formula is for the wheel, we can potentially look at a reaction on what pieces we need to build the wheel. Okay. The chemical reactions that we're working with in class, that's their intent. That's what they're trying to show you. They're giving you that formula. Why is it incredibly hard to do those kind of calculations? Because you can't just open up a book or open up a box and say, oh, look, there's a molecule of water. Okay? It doesn't work that way. Okay? We see a solution of water or a mixture of water and something else, and we just see one thing. We can't break up those tiny pieces. Okay? So what we have to do is come up with a symbolic notation that allows us to interpret and come up with those symbols. Okay. Let's take a look at some of these, I think. You want to take a look at these? How many moles of sodium hydrogen carbonate? We done this one yet? Yeah, we did do that one. Yeah, we did both those. So we'll just advance to the next concept. Okay, because we'll keep coming back to these things. We come up with this new concept of a limiting reactant concept, okay, which is a little bit kind of odd and everybody kind of panics about it. All that's happening with a limiting reactant concept is now doing those same calculations that we've been doing, but we have to do it 2 or 3 times and then compare our answers. Okay? So let's make some grilled cheese sandwiches. Okay? We're really simple grilled cheese sandwiches. Okay? Take a slice of cheese, 2 slices of bread, make 1 sandwich. Okay? So we got an equation. There's a nice little equation. Okay? 1 slice of cheese, 2 slices of bread, sandwich. If you have 5 slices of cheese and 8 slices of bread, how many sandwiches can you make? How are you going through and doing that calculation to get 4? So this comes back to formalizing the notation. We've been doing dimensional analysis and setting this up every single time. Guess what I want you to do with this question? Write it down. Give me that formal notation. Show me that your answer comes out to be 4. Okay? And we're going to make this a step more difficult. What I want you to do is write that notation on the board. As soon as you think you've got a notation that allows you to see that you only make 4 sandwiches, we got lots of pens, we got lots of boards. If you want to advance in the topic, it needs to get written down up on the boards. If it doesn't get written down on the boards, we don't advance in the topic, but the material keeps rolling through and it still shows up on the next exam. Okay? So speed is of the essence. I know, that's a couple conversions that came out of this. 2 slices of bread equals 1 sandwich. How do we know that? What our equation told us. It allowed us to do that conversion. Right. The other one 1 equals 1 slice of cheese. How do we know that? It's what the equation told us. What we're trying to do is convert bread into sandwiches. We're trying to convert cheese into sandwiches. Right? So we go through and we set up those calculations and we run them independent of each other. Right? When we look at our bread, 8 slices of bread generates 4 sandwiches. 5 slices of cheese generates 5 sandwiches. Why did you not tell me that we could make 5 sandwiches? That's 1 extra person that could have had a sandwich, and you guys are just sacrificing that and stealing that. What's the problem? Why can I not make 5 sandwiches? I've run out of bread. Bread is the limiting reagent in this calculation. Without bread, I can't make any more sandwiches. We still have to run that exact calculation twice. Look at what happens when we use just bread. Look at what happens when we use just cheese. How many sandwiches can I possibly get out of both of those? When I look at those answers, I now say which one is the smallest of those 2. Why? Because I'm greedy and I want to keep the other one to myself. No, there isn't another one to make. We've run out of materials. We can't make any more than the smallest amount. That is your limiting reactant concept. You all seem to get to that answer very, very quickly in your heads because we're really intuitive with things that we can grab and hold and move. Cheese, bread, sandwiches, we can all grab and hold and move those because they're probably one of the greatest things on the planet. Okay. But when we move to water, oxygen, hydrogen, mercury, those things we can't grab and hold those individual molecules. So it now all of a sudden changes and we freak out and think there's something different going on with it. It's the same thing as making cheese sandwiches. Okay. But to go through and do that, you now have to do more complex calculations because we're not looking at simply 8 molecules. I'm looking at 8 times 10 to the 23rd molecules. We're looking at a much larger scale. That scale is kind of hard for us to comprehend. So don't try and comprehend the scale. Work with the notations that are setting you up and allowing you to move through it and interpret those. Okay? Kind of, sort of? Too bad. This happened to actually be, whoa, come back here. Happen to be relatively simple. Okay, what we are converting to is moles of sodium hydrogen carbonate, right? From what?
Sodium carbonate.
Sodium carbonate. Do we know how much sodium carbonate we started with? 2. Is sodium carbonate the same as sodium hydrogen carbonate? No, so I need to do a unit conversion here. Moles of sodium carbonate. I wrote that formula wrong. To moles of sodium hydrogen carbonate. Why did I put those units in those locations? I want to be able to cancel. What numbers need to show up in front of those? 1 and 2. Where did you get 1 and 2 from?
The equation.
From the balanced equation. The 1 shows up in front of moles of sodium carbonate. How do you know that? You look at the number in front. It's 1. What number shows up in front of moles of sodium hydrogen carbonate?
2.
How do we know that? Because the number shows up in front. Punch it into the calculator. What do we get?
4.
We get 4. We then go through and we do it with, as I say, 2 moles of water. 2 2 moles of water. Okay? Because we're running low on time, I'm just writing it all out. We had 1 mole of water down below, 2 moles. Yeah, I know. That's why I said I'm doing it fast. Hydrogen carbonate gets us moles of sodium hydrogen carbonate. What's the number we get? 4 again. Okay, it's kind of boring. Do we have a limiting reagent at this point? No, because they will both produce 4. Last one. We have moles CO2. Since you asked about my unit thing, I'll go through and I'll do it that. And I want moles sodium hydrogen carbonate. How many moles of CO2 do we start with? Just 1. What's my conversion factor? Moles of CO2 need to show up on the bottom. Moles of the sodium hydrogen carbonate need to show up on top, right? What numbers need to show up? 1 mole of CO2 and 2 moles of sodium hydrogen carbonate. We go through and run the calculation. What do we get? We get 2 moles of sodium hydrogen carbonate. What is the most of sodium hydrogen carbonate that I can make? 4 is bigger than 2. Why do we say 2? I then run out of materials. Once I made 2, I have no more CO2. I can't make any more of the other ones. Right? So the maximum amount I could make would be the 2 moles of sodium hydrogen carbonate. What is the limiting reagent in this reaction? CO2 is now my limiting reagent because it's what's controlling the amount of product I produce. Last way we could ask that question. What is / are the reagents in excess? Sodium carbonate and water are our reagents in excess. Why? What does excess mean? You have too much. There we go. There's our reagents in excess. Could we push this even further?
Sure.
Yeah. One of the things we could ask is how much of our reagents in excess are left over?
I thought you were going to ask about the oxygen state.
No, I'm not going to ask about the oxidation state. We could potentially go back through and calculate that. Okay. It's processing each of those pieces and going through and doing it. We won't ask that question because that's a little bit too advanced. Okay. We aren't done quite yet. I know. Last thing we want to address is percent yields. Okay. We've gone through and done an experiment. You all did a great job doing this experiment. You yielded at the end of your experiment, you got 5 grams. Okay. Good job, 5 grams. I went through and did that exact same experiment. I got 50 grams. Did I do better?
Yeah.
When you guys did the experiment, you started with 5 grams. What would we expect as your maximum mass at the end of that? 5 grams. When I started the experiment, I started with 400 grams. Who did better? I got 50 out of 400. You got 5 out of 5. Who did better on that test? You did significantly better. The comparison of the raw numbers is completely meaningless. You have to have something compared back to for a theoretical maximum that you could have gotten out of it. If your difference between those two values is way off, then maybe something's wrong and you did something wrong. Okay? So we could scale experiments to change the raw numbers, but the result theoretically should never change. That's why when we run an experiment, we normalize our data. We normalize it by comparing it to our theoretical. What is the theoretical amount we could have gotten? So you may be asked to run a percent yield. When you do a percent yield, it is the actual yield that you obtained experimentally. We run through an experiment, I got 5 grams. Boom, that's your actual yield. What's your theoretical yield? Well, you sit down and you said, this is what I started with, this is how it propagates through the experiment. Theoretically, this is how much I could have made if everything went perfect. Okay. If everything went perfect, this is the number I get as my theoretical yield. The theoretical yield involves a calculation because you're guessing at how well it could have worked. The actual yield is not a calculation. The actual yield is something that you went in and said, oh, that's actually what it is. Okay. It's a number that's given to you by the instrument. To calculate a percent yield, you're now looking at the ratio between them. Okay? Your actual yield over the theoretical maximum. What are your units on your percent yield? Kind of whatever you're massing in. Okay? If we measure out grams, your actual yield is in grams. Could we do a percent yield by taking grams and dividing it by moles? You're theoretically supposed to get 5 grams of sodium carbonate. Your actual yield is 50,000 micrograms of sodium carbonate. When you do that calculation, 50,000 divided by 5, that's not going to be correct. What happens when we do your percent yields? Your units have to cancel. They have to be exactly the same. So what are the units on percent yield? There are none. It is unitless. Whatever you're doing for your percent yield, your actual yield units and your theoretical yield units must be identical. Okay? Does it matter what units you use? No. You can use grams, you can use moles, you can use liters, as long as the units for your actual and the units for your theoretical are the same. Okay? As long as you have that same unit, you are set and ready to run. We will pick up on Tuesday with lots more practice going through and doing longer versions of these questions.